Hello, welcome to the derivative. So we're going to start talking about derivatives, all right, which are half the study of calculus, through an important concept called the limit. Now the limit is needed for the definition of a derivative, so let's make sure you understand that really well. Okay, so we're going to look first at numerical or table type values and graphical graphs approaches to this first, and then we'll look at algebraically in our next section. Okay, so what is a limit? Let's look at an example. We're going to take the function f of x equals negative 2x plus 1. I'm even going to graph it over here on my Wabbit app. Y equals negative, make sure you use the negative, 2x plus 1. Let's graph that on a standard window. Okay, now I want to know what happens to f of x as x approaches 2. So whether I'm drawing here as x approaches 2, I'm getting closer and closer to, sorry, I shouldn't do that. I'm getting closer and closer to 2 on my x values. I want to know what's going on with the graph. Closer and closer to 2 with my x values, what's going on with my graph. But we're not going to look at this as a graph as much as we want to see it in table form. And on this TI graphing calculator, when you're in your tables, after you put a y equals, I am going to take my independent variable to ask. I'm not going to take it to 0. I'm going to pay attention. I'm going to go back to table set, and I'm going to take my independent variable to ask, hit enter, so that's the one it's flashing on. Now when I go to my table, it's going to ask me for the x value. Now, does it ask what's f of 2? No, we can find f of 2. That's pretty easy. F of 2 is negative 4 plus 1, which is negative 3. But it didn't ask for what's happening at 2. We don't care what's happening at 2. We want to know what happens to the y values as x gets close to 2. Do not care. It's like, I don't care. I've already decided I love this house, but now let me just take a look at the neighborhood. Ignoring the house, what does the surrounding area look like? So we'll use some x values that are super close to 2, but on the left, like 1.9. Now it's using my function that I put in y1, and I'll get a negative 2.8. I'm going to get closer to 2, and I see a negative 2.98. And I can get even closer to 2, right? Add more 9s, we're good. Oh my goodness, that looks like it's getting super close to negative 3. But what happens on the other side? What happens if something sketchy happens on the other side? Well, we have 2.1. Let's use a 1 instead of a 0 when I want a 1. And I'll get negative 3.2. 2.01, that's a little closer. 2.001, that's even closer. And look, it looks like that's getting close to 3, but on the top, right? Above, it's actually below negative 3. And this is above negative 3, right? But ignoring the signs, we're getting closer and closer to 3. We're getting closer and closer to 3. All right, so negative 3. So that we can conclude that when x is 2, suppose we don't know how to evaluate. We don't know that answer is negative 3. Using limits, we can conclude that the function is near negative 3 at that value. Now, I'm going to have a very important reason for this shortly. Why don't we just plug it in? I'll show you. But that's the concept. That's what we're looking at. Okay, so we're looking at what if you can't evaluate a function? Well, then what's going on around it has some impact on what that function value should be. It's like when your parents told you, you are who you're surrounded by. Yeah, that was just them trying to keep you away from hooligans. Very important. We don't plug in the value we are asking about because the question asks what happens as we approach. It does not ask what's happening at that value. All right, so let's look at a definition. If f of x approaches the number L as x approaches, okay, so in this case, L would have been the negative 3. our y values approached the number -3. As x approaches, but is not equal to a from both sides, in our example, our a value was 2. Then we say that f of x approaches L as x, and then this arrow to a says x approaches a, or that the limit of f of x as x approaches a is L. This notation, and when I write it by hand, I'll frequently write it with the limiting value down below. The limit as x approaches a of f of x equals L. Same thing, all right? Usually we'll write it stacked, but when it's in typing, it's just, I prefer this way. But when the time that I wrote these notes, I didn't know my keyboard as well as I should have. So the limit as x approaches a of f of x equals L. The limit as x approaches a of f of x is L. So it tells us here the x is getting close to a, the f value is getting close to L. If f of x fails to approach a single fixed number as x approaches a from both sides, then we say that f of x has no limit as x approaches a, or the limit as x approaches a of f of x does not exist. A single fixed number. So if I look at the function 1 over x squared, this is what I call a volcano function. As x approaches 0, right, as I get closer and closer to 0 from the right, my function blows up. As I get closer and closer to x equals 0 from the left, my function blows up. That's not a number. Infinity is not a number. If I look at the very popular graph, I'm just going to tell you right now, know this. This is going to come up time and time again. By the time we get to chapter 11, write this down. It's even important enough for me to change. This is an important one. If we look at the graph of the square root of x over x, notice that x cannot be 0. We can't put 0 in because we cannot divide by 0. Well, mere mortals can't, but you will be able to shortly. So there's open circles at 0, but if x is positive, it's positive over positive. And if x value is negative, then we'll have a positive divided by a negative. So the answer is 1. It's just a difference between whether it's positive 1 or negative 1. But as I come in to the x value of 0 from the right, my y value is up here at 1. As I come into the x values getting closer to 0 from the left, wow, that was harder all of a sudden, then I see that my y values are getting close to -1. This is not a single fixed number, right? There's two different answers. Here there is infinity, a symbol. Here there's two different answers. If we look at a graph such as the limit as x approaches 2 of 1 over x minus 2, this is what our graph will look like. As we get closer and closer to 2 with our x values, so I'm going close to 2, and I'm going close to 2, what happens to my y values? I want to take it off of that red now. Let's go back to blue. Well, here my y values go off to infinity. But as I get close to 2 from the left side, to the left of 2, I see that these values go to -infinity. So two different values, and they're not even fixed numbers, so that's definitely not going to work. All right, that's a lot of writing, so let me take some of it off so you could see what the original was, just in case. I'm going to leave that part though. All right, the limit. All right, scrolling on. In another useful kind of limit, we let x approach either positive or negative infinity, by which we mean we let x get arbitrarily large in either direction. Oh my goodness, I'm looking at how useless these notes are. I'll do a follow-up video to this one with a couple more examples. For example, let's find the limit as x approaches infinity of 3x squared minus 2 over x squared plus 7. I'm going to turn my calculator back on and then go back to y equals. Let's enter our function, the numerator in parentheses, 3x squared minus 2. I don't know why I'm doing this the hard way. Oh yeah, I remember. It turns out Desmos is awesome for most things, but I haven't fully integrated myself with the tables yet. I guess I could do this table feature. Yeah, I could totally do this on Desmos. We should have done it on Desmos. The other examples I record next will have Desmos instead of the calculator. All right, so now x is not getting closer and closer to 2, it's getting closer to infinity. But how do we get close to infinity? We start with an input of 1 and get bigger. If I'm going to infinity, I'm hitting all the powers of 10. Look at that. Wait, what's going on? Did I do it right? It looks like I went from 0.125 to 2.78 to 2.99, and then this just says 3. Let's take a look. You could actually use this. Look at that. Right? So quickly, our limit is seen. It's very easily seen as 3. So as x goes to infinity, we know that this function is going to settle on 3. What might that look like? It looks horrible right here. Actually, we can see it already. It's going to 3 quite quickly. All right. Now, the graph allows us to see limits without having to evaluate a bunch of numbers. To decide whether the limit as x approaches a of f of x exists and to find its value if it does, we're going to draw the graph by hand or with a calculator. Position your pencil point or the trace cursor on a point of the graph to the right of x equals a. Right, so you're to the right of, say we're looking at x equals 3 here. As we move in, you'll want to move your finger on your screen, move your cursor. Depends on if you have a touch screen or not. And to the left of x equals a, and look independently. If the left and the right both have the same value, then you've found the limit. Repeat steps 2 and 3, this time starting... What? And we just randomly drop some notation on you here. I can't even read my own notes. The limit as x approaches a with a little positive up here of f of x, that says the limit from the right. This. Alright, it says the limit from the right. So that notation is easy to remember if you consider that in a number line, and we're looking at 0, positive numbers are on the right, negative numbers are on the left. So we might also have right here, as we're approaching from the left, the limit as x approaches a from the left, so we'll use the negative sign to indicate left of f of x. Limit from the left, so we'll look just as we're coming in from the left, what's that number? We'll look as we're coming in from the right to our value a, what's that number? So we found the limit from the right, we found the limit from the left, and if the limit from the left and the limit from the right both exist and have the same value, then the limit exists. It doesn't matter what f of a is. It doesn't matter what's happening at that point. We only care what's happening near that point. Also, if you want to evaluate the limit as x approaches infinity, just keep going far right on your graph. Like let's jack this up here a little bit to 100. And I'm going to change my scale a little bit just so it's not ugly looking. Oh yeah, right? I can trace that out. That's going to be the same value. That's a 3. For the limit as x approaches negative infinity, that's an x approaching negative infinity. Move the pencil towards the far left of the graph. If x equals a happens to be an endpoint in the domain, then only a one-sided limit is possible. All right, so if the domain stops at 4, we can only find the limit from the left because there's nothing in the domain on the right side of 4. All right, these are very limited sketchy notes, so I'm going to do a second video on this one called examples. I'll get to it as soon as I can. Thanks for watching.